So let's work an example of an ideal gas. This is an area where the density changes, and so when we use rho GH in non-differential form, we get bit because the density changes. So how are we going to handle that? Just to remind you what I'm talking about here, we're looking at the differential form of fluid statics, which looks like this: dp dx equals 0, dp dy equals 0, and dp dz is equal to minus rho g, assuming that gravity is acting in the z direction downward. But for an ideal gas, well, we saw before that you could integrate this real quick and get, for a constant density and constant value of g, this is just P2 is equal to P1 plus rho GH, the thing we're used to. But here it's not, because density is going to change. So let's look at ideal gas, which says that pressure is equal to density times gas constant times temperature, T. All right, so to solve this, let's start. We don't really care about the x and y. Let's just do the z direction here. We can multiply this up, right? So if we start with dp dz equals minus rho g, then we can write that dp is equal to minus rho g, dz, just by multiplying up. But for an ideal gas, the density here can come from the ideal gas equation of state, right? Rho is equal to P over RT. And so what that substitution gives us is a new thing that looks like dP is equal to minus P over RT G dz. This is a differential equation now that we need to solve. Thankfully, it's separable. And so get all the p's on one side, everything else on the other, and integrate. So we're going to write this as dp over p on that side, and on the right-hand side we'll be left with minus g over rt dz. And now it's time to integrate. So we're going to integrate this side from p1 to p2. We're going to integrate this side from z1 to z2, and we're going to assume constant g and t. R always is constant because that's from the ideal gas equation of state. And so what that lets us do is pop these things out. On the left-hand side, the integral of dp over p, well, that's just the natural log of p2 minus the natural log of p1. And on the right-hand side, we're left with minus g over rt. Those all pulled out of the integral, and then you're just left with the integral of dz, which is z2 minus z1. Remember that for natural logs, the difference of two natural logs is the same as dividing them inside, and so we can write the natural log of p2 over p1 is equal to minus g over rt z2 minus z1. Or we could take the exponential of both sides of this to get this in terms of just p2 over p1 equals exponential minus g over rt z2 minus z1. And so this is an example of how you can use the more formal fluid statics definitions to calculate the pressure in a situation where maybe things like the density aren't constant. Here we let density change, but also we could have looked at what would have happened if g and t had changed as well, and it would have been that we'd need equations to substitute for them before we could integrate.